the deep dive. Today, we're not just dipping our toes. We are plunging headfirst into one of the deepest, most fascinating currents in mathematics, the world of prime numbers.
Absolutely. These numbers, they're fundamental, right? The building blocks.
Exactly. Only divisible by one in themselves. But they're also, well, they're dazzling, yet so stubbornly unpredictable. It's like they appear almost randomly across the number line.
And mathematicians for centuries have just been captivated trying to figure out the pattern, the dance.
The cosmic dance, I like that, trying to decode where the next prime will show up.
Mm.
And in that epic quest, there's this one tool that stands out. It's incredibly powerful, but also endlessly enigmatic.
The Riemann zeta function.
That's the one. It really is central.
So our cornerstone for today's deep dive is a truly monumental work, The Theory of the Riemann zeta function by E.C. Titchmarsh. We're looking at the second edition, which was meticulously revised by D.R. Heath Brown.
And this isn't just, any textbook. No, not at all. We've actually taken a proper deep dive into the physical book itself. We've looked through its prefaces, we've scoured the editorial reviews, charted out its incredibly detailed table of contents. It's at this reputation, right? A definitive encyclopedic reference.
Definitely. And crucially, it's often called the most cited book on the zeta function, but with a key qualifier.
Ah, yes, that phrase, for its time.
Exactly. That phrase, for its time, is incredibly significant, and it's actually the key to what we're doing today. Our mission isn't just to summarize this colossal work.
It's huge.
It is. We want to truly grasp its unique historical position. Where did it stand in the landscape of mathematics? So we'll explore precisely what it covered comprehensively, what was really nailed down, understood, by the time of its last revision. That was 1987.
Right, 1987, that's our cutoff.
Precisely. And then, using that date as our boundary, we'll sort of logically infer. We'll discuss what's missing from its pages, what were the new horizons, what discoveries popped up in the decades after 1987, and we'll always keep the book's own contents as our reference point.
Okay, I get it. So it's like we have this perfectly preserved, incredibly detailed snapshot of a really vibrant, evolving field,
Yeah,
but taken at a very specific moment, 1987.
exactly. A complete inventory of knowledge up to that point.
What an exciting way to explore not just what was known, but how mathematical knowledge actually builds and expands over time. It leaves these gaps, these new questions, new territories to discover.
Fantastic. Okay, let's unpack this incredible book and see where it stood and maybe what it launched. All right, let's start right at the beginning. The absolute heart of this. The Riemann zeta function itself. You hear it described all the time as our most important tool in the study of prime numbers. But, for those of us who like the why, what makes this function so utterly fundamental? Why is it so indispensable in this centuries-old quest? Well, it's truly remarkable because the Riemann zeta function manages to embody both additive and multiplicative structures, all within a single, quite elegant mathematical framework.
Additive and multiplicative together.
Yeah. Yes. Think about that. It connects the world of sums, how numbers combine when you add them, with the world of products, specifically products involving prime numbers. This dual nature, that's what gives it such profound significance in number theory.
Okay.
If you open Titchmarsh's book, Chapter 1 is titled, very appropriately, The Function and the Dirichlet Series Related to It. Right from the get-go, it dives into the definition of S. Now, that zeta of chess is usually defined as this infinite sum, 1 over 1 to the power s, plus 1 over 2 to the s, plus 1 over 3 to the s, and so on, forever.
An infinite series.
Right, a specific type called a Dirichlet series. It involves powers of integers. But then, and this is the magic, the book immediately shows you how this exact same function can also be written as an infinite product. But this product isn't over all integers, it's only over the prime numbers.
Just the primes.
What?
Wow.
Yes, that's the famous Euler product formula. It directly links the additive structure, the sum, to the multiplicative structure, the product over primes. It's like a bridge.
A bridge between adding numbers and multiplying primes.
Precisely. And that connection is the source of its immense power. It means that by studying the properties of this function often in the complex plane, which lets us use both real and imaginary numbers, giving us more room to work.
Okay.
By studying it there, we gain insights into the distribution of prime numbers, which are inherently multiplicative creatures. Titchmarsh's approach, right from Chapter 1, even mentioning things like Ramanujan sums. These are complex sums tied to number theory. It just shows the meticulous groundwork he laid. Understanding these foundational bits reveals the function's intricate properties.
So it's like having a secret decoder ring, translating patterns from addition into insights about prime multiplication.
That's a great way to put it, a universal translator, almost. It lets us see how the additive side informs the multiplicative prime side. It's an incredibly powerful bridge.
That really clarifies it. And speaking of hidden patterns and secrets, this book, even the updated 1987 edition, makes it clear that the famous and still unsolved Riemann hypothesis at its heart is a central theme. It's right there, presented as this enduring mystery, even in 87.
Oh, absolutely. The Riemann hypothesis isn't just a problem in math. For analytic number theory, it's arguably the problem. It's been steering research for, well, over a century and a half now, since Riemann proposed it back in 1859.
Wow, that long.
Yeah. So a book dedicated to this function, especially one aiming to be this comprehensive, simply has to put the hypothesis front and center. People often call it the Everest of number theory.
Because it's so hard to climb.
Exactly. Both incredibly difficult and the view from the top, the implications, if it's true, would be profound.
So what is it, in essence? Can we demystify it a bit?
Let's try. Basically, the hypothesis is about the zeros of the zeta function. These are specific points, complex numbers, where the function's value becomes zero. These zeros aren't just random. They hold information about the primes. The non-trivial zeros are the interesting ones.
Okay, the important zeros.
Right. And the Riemann hypothesis postulates that all of these non-trivial zeros lie on a very specific line in the complex plane. Imagine this vast mathematical landscape and all the important landmarks, these zeros, are perfectly aligned on this one single critical line.
All of them. On one line.
That's the conjecture. If it's proven true, it would be like finding the ultimate map to the primes. It would give us incredibly precise estimates for where prime numbers appear. And not just that proving it would instantly validate maybe hundreds of other mathematical conjectures that currently rely on it that assume it's true.
So it's a linchpin for a huge amount of mathematics.
A massive linchpin. And what's fascinating reading Titchmarsh in 87 is that sense that even then, decades after Riemann, it remained the central, driving, unsolved problem.
Standing.
Still standing. Which raises that interesting question. How does research around a hypothesis like this evolve when the core problem itself resists solution? The book, in effect, becomes this incredibly detailed record of the best attempts, the sharpest tools, the deepest insights achieved up to 1987, all developed in the shadow of this grand unsolved puzzle. It maps out everything known about the zeros distribution and their implications right before whatever comes next.
It really is the Everest, then. I remember reading that quote from David Hilbert, the great mathematician. Someone asked what he'd do if he woke up after 500 years.
Yes, the famous quote.
He said, I would ask, has someone proved the Riemann hypothesis? It just perfectly captures how central and enduring it is.
It really does.
And the editorial reviews for Titchmarsh's book really hammer home this point about its nature, don't they? Calling it a definitive encyclopedic reference and noting it's not a book you read cover to cover, but one you consult.
Yeah, that's key.
Packed with a vast collection of theorems, results, and techniques. That sounds less like a story and more like, well, an indispensable toolbox.
That's a very sharp observation. It absolutely captures the essence of Titchmarsh's approach. No, you definitely don't curl up with this one for a casual read.
Not exactly beach reading.
Not unless you're a very specific kind of mathematician. Its consultative nature means it's a comprehensive compilation of established knowledge. It's a robust toolkit for researchers. You don't read it cover to cover. You dive into specific sections when you need to understand a particular proof, or track down a specific technique, or find the history of a certain result.
So it solidifies its role as a benchmark.
Precisely. If you were tackling a new problem, say about prime distribution, you'd pull Titchmarsh off the shelf. You'd check what methods are already known, what's been rigorously proven, what tools are available, and the table of contents itself is like a guided tour through analytic number theory. It showcases the incredible scope. You see chapter titles like The Analytic Character of Sus and the Functional Equation. That's not just defining the function, it's about extending its definition, using something called analytic continuation to make sense of it over a wider range of complex numbers. That's crucial for uncovering its deeper secrets.
Okay, extending its reach.
Exactly. Then there's the theorem of Hadamard and de la Vallée-Poussin. These are fundamental results that together proved the prime number theorem. That theorem is a cornerstone. It gives us an approximation, a sort of large-scale estimate for how many primes there are up to a certain number.
A foundational result.
Absolutely. And then you have chapters like approximate formulae. These are essential because often you can't calculate the zeta function exactly, especially for complex arguments, but you can find formulae that get you incredibly close, which is vital for both theoretical understanding and practical computation. These titles alone just convey the immense breadth of fundamental areas Titchmarsh covered so meticulously. He set the standard for decades. It's a real monument to rigorous scholarship, compiling centuries of work.
So it really is the kind of book you'd keep right there on your desk if you worked in this field, always within reach.
Without a doubt.
And it's interesting, too, that even the first edition, way back in 1951, it already acknowledged its own limitations. The preface to that original version apparently noted some areas were scantily represented. It specifically mentioned some theorems on primes and the work of A. Selberg and Vinogradov.
Yes, Adel Selberg and Ivan Vinogradov. That's a really important detail. It provides this crucial historical precedent showing how all of mathematics really constantly evolves. Even a work striving to be definitive is still a snapshot in time.
Right.
The fact that Titchmarsh himself pointed out these gaps shows how dynamic discovery is. Selberg, a Norwegian mathematician, did groundbreaking work on sieve methods techniques for counting primes, and he famously gave an elementary proof of the prime number theorem, meaning one that didn't rely on complex analysis, which was a huge surprise.
Wow.
And Vinogradov, a Russian mathematician, developed incredibly powerful methods for estimating things called exponential sums. These sums are fundamental tools in analytic number theory for tackling problems about prime distribution and related areas. Their work was absolutely cutting edge in the mid-20th century.
So Titchmarsh knew this important stuff was happening.
Exactly. His honest appraisal meant he recognized its significance, even if his first edition couldn't fully integrate it all just yet. It really hints at that continuous process of research where new discoveries are always building on and sometimes dramatically expanding or even correcting what came before.
So even from the very beginning, Titchmarsh, the original author, he knew that this sprawling field was always moving, always growing. It really makes you wonder what else would need updating down the line, and what completely new ideas might pop up later. And that's just the perfect segue, isn't it? Because Titchmarsh's original work did get that major update. The second edition, published in 1987. Well, it wasn't just a reprint with corrections. It was a truly significant revision. The description says it has been revised to include descriptions of work done in the last 40 years and is updated with many additional references.
40 years. That's huge.
And the editor, D.R. Heath Brown, added some 120 additional references to the more recent literature. That sounds like a massive undertaking, basically integrating a whole career's worth of new research into one update.
It really is a monumental effort. And it deeply underscores just how incredibly dynamic mathematics is, especially in a fast-moving field like analytic number theory. 40 years. That's roughly 2 generations of mathematicians, right?
Yeah, easily.
And the fact that Heath Brown meticulously integrated such a vast amount of new research, adding those 120 references, it means he went to extraordinary lengths to keep the book very comprehensive, to make sure it covered, as the review said, nearly anything anyone would want to know about the zeta function. But, crucially, up to that specific point, 1987.
Right, that 1987 horizon again.
Exactly. This wasn't just tweaking things or adding a bibliography. It was a deep infusion of new knowledge, brand new techniques, refined understandings that had developed since Titchmarsh's original 1951 publication.
You can really feel the weight of that update.
You can, and you see the rigor involved when you look at the editor's acknowledgement in the preface to the second edition. He thanks prominent mathematicians like J.B. Conry, H.L. Montgomery, S.J. Patterson. These aren't just random names.
No, they're big figures in the field.
Absolutely. Some of the leading figures in analytic number theory at the time. Their mention indicates the caliber, the depth of the updated research that Heath Brown was carefully weaving into the existing fabric of the book. And there's even a specific mention, like recent results described in the end of chapter notes may be found in the book by Ivich III. This shows he was carefully cross-referencing, integrating the very latest scholarship available then, making sure it was current and complete for its time. It's like the book was a living document, adapting and growing.
That's incredible. So it wasn't just a historical artifact. It was actively being brought back to the cutting edge of mathematical thought for that era. With such a huge infusion of knowledge over those 40 years, what kind of new frontiers were being explored? What specific areas saw major progress that made it into this 1987 edition?
Well, the table of contents itself gives us a fantastic roadmap of these expansions and refinements. It really highlights the specific battlegrounds where new insights were being won. For instance, you find sections like the order of Dus in the critical strip.
Okay, the critical strip.
Gotcha.
Sounds important.
It is. Without getting lost in the complex plane, just imagine the zeta function lives in this special mathematical space. The critical strip is a particular vertical region within that space where all the really important non-trivial information about primes is thought to reside, including those mysterious zeros.
Got it.
So Titchmarsh, in its updated form, details highly specialized tools methods named after mathematicians like van der Corput and Vinogradov, which are essentially advanced analytical techniques. They help us understand how big or small the zeta function can get inside this crucial strip. Pinning that down is critical if you're trying to understand the primes.
Okay, measuring its behavior in the key zone.
Precisely. Then you have things like mean value theorems, covering higher moments convexity, Atkinson's formula. Now, think of the Riemann zeta function as maybe a wild, chaotic ocean. Trying to predict every single wave, every value, is incredibly hard, maybe impossible. That's where mean value theorems come in. These are sophisticated tools for averaging the values of the zeta function over certain regions or lines. Instead of predicting individual waves, mathematicians use these methods to understand the overall currents, the average behavior of that mathematical ocean. Higher moments are like taking more complex averages, convexity relates to the function's overall shape, and Atkinson's formula is a famous, highly precise tool for calculating these mean values. This gives remarkably powerful insights into how the function behaves on average, which is often more tractable and just as revealing as chasing every single unpredictable fluctuation when searching for prime patterns.
That makes the abstract much more concrete. So these aren't just new facts being added, but entirely new ways of looking at the function, new powerful mathematical lenses.
Exactly right. New perspectives. The book also expands significantly on the general distribution of zeros. It includes things like Selberg's bound and Halas's lemma. This shows progress in understanding not just that zeros exist, but more precisely where they tend to lie, how many there are in certain regions, how they cluster together. Selberg's bound, for instance, gave important estimates on the number of zeros near that critical line. Halas's lemma is a technical but powerful tool for estimating sums related to Dirichlet series, which directly impacts our understanding of these zeros.
Getting more precise about where the zeros are.
Yes, and of course, a really critical area is the zeros on the critical line. This section features things like the Hardy-Littlewood hypothesis, which is a conjecture about how many zeros should be on the line, and Levinson's method. Now, Levinson's method was a landmark achievement from the 1970s. It provided the first rigorous proof that a positive proportion, actually, more than one-third of the non-trivial zeros do lie exactly on the critical line.
Wow. So proving a chunk of them are right where Riemann guessed.
Exactly. A major step towards the full Riemann hypothesis, even if it didn't prove all of them were there. The book also discusses zeros of derivatives of the zeta function, extending the inquiry into its finer analytical properties.
Okay.
And finally, there's a section on consequences of the Riemann hypothesis. This details what would be true if RH is proven. It mentions things like Montgomery's pair correlation conjecture.
Montgomery. I think I've heard that name.
Yes, Hugh Montgomery. His work, based on conversations with physicist Freeman Dyson, suggested a completely unexpected connection. The spacing between the zeta function zeros seemed to statistically mimic the spacing between energy levels in complex quantum systems, like heavy atomic nuclei, which are described by something called random matrix theory.
Wait, quantum physics.
Yeah. A mind-bending link that really took off later, hinting at potentially deep connections between number theory and physics. The book also mentions the disproof of the Mertens conjecture, which was a related but ultimately incorrect guess about the behavior of a certain number-theoretic function, showing that even exploring the consequences of RH could lead to surprises. And Turan's hypothesis, another related conjecture about the function behavior.
So much ground covered.
Absolutely. Each of these areas, the critical strip, mean values, zero distribution, the critical line itself, the consequences represents frontiers of active research throughout the mid-20th century. The inclusion of names like Selberg, Vinogradov, Hardy, Littlewood, Levinson, Montgomery, Mertens, Turan. It really highlights the profound theoretical developments shaping the understanding of the zeta function and its intricate link to primes. If you connect it to the bigger picture, each specific area was like a battlefield where new techniques, deeper insights were constantly being forged. Heath Brown's revision essentially curated the victorious strategies from 4 decades, presenting them as the established wisdom of 1987.
Wow, it really sounds like an incredible synthesis of decades of intense intellectual effort. So this wasn't just adding facts. It was integrating entire new methodologies and perspectives that had emerged, fundamentally deepening the field's understanding. And I noticed something else that caught my eye. The book also touches on p-eta zeta functions. It's in Chapter 2, under the analytic character of this and the functional equation. And there's even a footnote mentioning p-eta integers and p-eta zeta functions linked to Leopold and Kubota's work. What's that about?
Ah, that's a fantastic observation. And it's quite significant because it points to the broadening scope of the field itself. Including p-eta zeta functions shows that by 1987, the connections between the classical Riemann zeta function we've been discussing and the world of p-adic analysis were already recognized, already being explored. This isn't just a minor detail. It shows mathematics reaching beyond classical analysis into more abstract algebraic structures.
P-adic, what are p-adic numbers briefly?
Okay, briefly. Imagine a different way of measuring distance between numbers. Instead of the usual distance on a number line, you measure distance based on divisibility by a specific prime number. Let's call it p. So in the 5-adic numbers, for example, numbers divisible by 5 are closer to 0 than numbers not divisible by 5. Numbers divisible by 25, which is 5 squared, are even closer, and so on. It creates a completely different geometry for the integers.
A weird kind of closeness.
It feels weird at first, yes.
Yeah.
P-adic zeta functions are analogs of the Riemann zeta function, but defined using these p-adic numbers. They share some similar properties, but are used to study arithmetic questions within this p-adic framework. The work of mathematicians like Leopold and Kubota in the mid-20th century was really foundational in building these bridges between the classical and p-adic worlds.
So even by 87, the book was showing these connections.
Exactly. It demonstrates that mathematicians were already looking beyond the familiar complex plane for insights, suggesting this rich interplay between different mathematical disciplines. It was expanding the very notion of what a zeta function could be.
Okay, here's where it gets really interesting for our purposes today. This book isn't just about the classic zeta function. It's already reaching out, touching these other more abstract mathematical worlds like p-adic numbers. It's a great reminder that mathematics is never truly isolated, right? It's this vast interconnected web. Discoveries in one corner often shed light on another, which makes you wonder, how much more would those connections deepen after 1987? And that brings us perfectly to the most intriguing part of our deep dive, the real core of what we wanted to explore today. What's not in this incredible book, we've established Titchmarsh, revised by Heath Brown, is the definitive encyclopedic reference of its time. And that time, we keep saying, is 1987. Specifically, the preface for the second edition is dated February 1987. So that sets a very clear, very sharp chronological boundary. What can we actually expect to find inside its, 400-odd pages?
Precisely. That phrase, of its time, isn't a criticism. It's a vital historical marker, a timestamp. It implicitly tells us that any major developments, new theorems, huge shifts in research paradigms, maybe even entirely new subfields that blossomed after February 1987, well, by definition, they're going to be missing from this book.
Not because the book is flawed, but just because time moved on.
Exactly. It's not a flaw. The book remains a foundational masterpiece, an invaluable resource. It's simply an acknowledgement of how rapidly a living, breathing field like analytic number theory progresses. New ideas are constantly bubbling up, challenging, refining, expanding upon the existing knowledge base, pushing the boundaries. And this raises that crucial question. If a book is definitive of its time, that means the field kept flourishing beyond that time. So what new frontiers would emerge? Building on this incredibly strong foundation laid by Titchmarsh and Heath Brown, but stretching into entirely new territory that maybe even they couldn't have fully foreseen back then.
And one of the biggest elephants in the room, the biggest unanswered question the book itself puts front and center, is the Riemann hypothesis. It explicitly states it's still unsolved. Given that status in 1987, it's an absolute certainty that research on this specific problem has continued intensely, relentlessly in the decades since. So what's missing there? What new insights, new approaches, new tools might mathematicians have brought to bear on this monumental challenge since this book was last revised?
Absolutely. The Riemann hypothesis being the holy grail, it would naturally be the subject of just relentless inquiry post-1987. Now, obviously, the book can't contain a solution that hasn't happened yet.
Still waiting for that.
Still waiting. But what it wouldn't include are the innovative theoretical approaches that have really gained traction since then. For example, we mentioned those surprising connections with quantum physics and random matrix theory.
Right, the Montgomery-Dyson thing.
Exactly. That whole area of study, exploring whether the statistics of the zeta zeros truly mirror the energy levels of complex quantum systems. That became a major research program after 1987. It offered entirely new ways to think about the problem, new angles of attack.
So that whole perspective would be largely missing.
Largely missing, yes. The book also wouldn't feature the results of new, much more sophisticated computational checks. People have used vastly more powerful computers since '87 to search for counterexamples to the Riemann hypothesis, verifying it for trillions and trillions of zeros, pushing the verification boundary much, much further up the critical line than was remotely possible back then.
Okay.
Nor would it include new conditional results. These are theorems that mathematicians prove by assuming the Riemann hypothesis is true. Establishing these results builds up this whole network of consequences, showing just how much structure RH imposes on the mathematical world. Many significant conditional results have been proven since 1987.
So even if RH isn't proven, we know more about what would happen if it were.
Precisely. The decades since '87 have definitely seen mathematicians explore different angles, developing new conjectures, building on Montgomery's work, perhaps even exploring entirely novel mathematical frameworks. And let's not forget, the Clay Mathematics Institute offered its $1 million prize for a proof of the Riemann hypothesis in 1998, well after this book's revision. That certainly didn't hurt motivation,
$1 million tends to focus the mind.
doesn't it? So the book serves as this fantastic historical snapshot of the state of the art on the RH problem in 1987. It shows the powerful techniques available then. But the story of the Riemann hypothesis, well, it kept going, and it continues today, with new chapters constantly being written, theoretically and computationally.
It's fascinating. Imagine a team of mathematicians in 1987 poring over this very book, using its theorems, its methods, then looking out at the future, wondering if their work, or maybe their students' work, would be the one to finally crack it. What new tools did they dream of? What breakthroughs were they hoping for, maybe tied to technology they couldn't even imagine yet?
That's a great thought experiment.
And that leads us right into another area where this book, just by its publication date, would inevitably show its age: computational power. The book does have Chapter 50, calculations relating to the zeros, and it mentions results of computer calculations. But I mean, computer calculations in 1987, that's a different universe from today, right? What exactly is missing from its pages when we think about the explosion in digital power since then?
Oh, indeed. The computational landscape has been utterly, completely transformed since 1987. The sheer amount of computational power available for rigorously searching for those zeros on the critical line, for testing related conjectures with incredible precision, for doing large-scale numerical analysis. It was orders of magnitude less, maybe exponentially less than what became possible just a decade or two later, let alone now.
Orders of magnitude.
Easily. So the book, by necessity, only reflects the computational state of the art before 1987. This implies a huge missing area. The explosion of raw processing power, yes, but also the development of new, highly optimized algorithms specifically designed for finding and verifying zeta function zeros. And then there are the massive distributed computing efforts.
Like using thousands of computers together.
Exactly. Projects like ZetaGrid, which launched in the early 2000s, harnessed the collective power of thousands, maybe tens of thousands of ordinary personal computers volunteered over the internet. They used this power to verify the Riemann hypothesis for the first, say, 10 trillion zeros, then more, pushing the limits of verification far, far beyond what anyone could have dreamed of doing in 1987.
10 trillion zeros.
And it's gone further since. These efforts didn't just confirm the hypothesis for more zeros, they generated unprecedented amounts of data. This data allows mathematicians to look for new, perhaps very subtle, statistical patterns in the zeros distribution. This includes advances in the precision and speed of the calculations themselves, and more recently, you see the beginnings, the nascent application of AI and machine learning. People are trying to use AI to look for patterns in the zeros, or even to help generate new conjectures. That kind of approach was basically science fiction in 1987.
AI looking for prime patterns.
Wow. It's early days, but it's happening. These computational breakthroughs are crucial. They bolster our confidence in RH by showing it holds for vast numbers of zeros, and they might uncover unexpected clues that could lead towards a theoretical proof. All of that post-1987 computational story is, naturally, absent from Titchmarsh.
It's just astonishing how technology can reshape the very methods of mathematical discovery itself. The scale difference is mind-boggling. And, sort of relatedly, the book specifies its target audience: postgraduates and workers in analytic number theory and classical analysis. Now, it's incredibly thorough in those core areas, clearly. But mathematical fields, they rarely stay completely isolated, do they? Has the Riemann zeta function forged even deeper, maybe more surprising, interdisciplinary connections after 1987? Connections that wouldn't be in a book focused so tightly.
That's a crucial point, and yes, it's definitely an area of missing content. While Titchmarsh and Heath Brown's work is an absolute masterclass in its stated domain analytic number theory and classical analysis, mathematical fields are profoundly interconnected. And since 1987, analytic number theory, and the zeta function specifically, has continued to forge deeper and often quite surprising links with other branches of math and even other sciences. The book's scope naturally wouldn't extend to capture these newer interdisciplinary dialogues and the fresh insights they've generated.
Like what, for instance?
Well, we touched on quantum chaos and random matrix theory already. That connection became much more widely accepted, much more deeply explored post-1987. The idea that the statistics of zeta zeros eerily match eigenvalues of random matrices, which model quantum energy levels, that moved from a curious observation to a major research direction.
Okay, that one's solidified.
Definitely. The book also wouldn't delve into the expanding relevance of zeta functions and their generalizations called L functions in areas that really matured or exploded after 87. Think about information theory, complex network analysis, or even advanced cryptography that developed alongside the internet age. Zeta functions pop up in unexpected ways there.
Cryptography.
In some advanced areas, yes.
Yeah.
The deep properties of number fields, which are related to zeta and L functions, can sometimes play a role, and theoretical physics has continued to find resonances. Zeta functions appear in calculations in string theory and quantum field theory, often as mathematical tools needed to handle infinite sums or products that arise naturally in those physical models.
So its influence spread wider.
Much wider. These connections represent those new horizons that emerged, sprouting from the incredibly strong foundational work laid out so meticulously in Titchmarsh. The zeta function acts like the central node, and new branches of inquiry just naturally grow out of it, reaching into seemingly disparate fields. That richness of interconnection, especially with fields that boomed post-1987, is a significant part of the missing story.
That makes perfect sense. The stronger the foundation, the more ambitious and diverse the structures you can build on top of it. So beyond these new connections and the computational leap, what about the core tools themselves? The techniques within analytic number theory. The table of contents details methods like Vinogradov's method, approximate formulae, sieve methods. The preface even mentions Selberg and Vinogradov's work being initially scantily represented, but then included in the second edition. Surely these methods didn't just stop evolving in 1987.
Oh, absolutely not. And this is another significant area of post-1987 advancement that, by necessity, isn't captured in the book. The techniques detailed there, Vinogradov's powerful method for estimating exponential sums, the various approximate formulae for the zeta function, the ingenious sieve methods used for counting primes in various sets. These were state-of-the-art in 1987. They were incredibly powerful. But mathematical methodology is a living thing. It's constantly being refined, sharpened, generalized, and applied in more sophisticated ways.
It never stands still.
Never. After 1987, these existing tools were subjected to decades of further intense scrutiny and innovation by brilliant mathematicians. This led to significant refinements, yielding even sharper estimates, broader applicability. We've seen, for example, the development of even more powerful and versatile sieve methods. Think of work by people like Henryk Iwaniak or major theorems like the Bombiri-Friedlander-Iwaniak theorem, which allow us to tackle deeper problems about primes in specific sequences like arithmetic progressions that were previously out of reach.
So the tools themselves got better.
Much better, much sharper. There's also been a deeper understanding of mean value theorems, not just for the Riemann zeta function itself, but for the whole vast family of related functions called L functions. These generalizations of the zeta function are really at the forefront of modern number theory, and understanding their average behavior is crucial. And of course, new analytical techniques for deriving approximate formula or for studying the higher moments, complex averages of the zeta function. These have been discovered or perfected in the post-1987 era.
So the toolkit expanded.
Dramatically. The book's further references section, while excellent for 1987, would have just exploded exponentially in the intervening decades. It would point towards all these new theoretical and methodological developments, tools that allow researchers today to tackle problems that might have seemed completely intractable back then.
So what we're really seeing here isn't just a story about what's in this amazing book, but also what it inspired. This comprehensive reference became this absolutely essential launchpad, didn't it, for future generations to take these very tools, refine them, sharpen them, ask new questions, and just see where these powerful ideas could go next.
That's exactly right. It's a testament to the enduring power of fundamental research. Even when grappling with a colossal unsolved mystery like the Riemann hypothesis, the surrounding work, the development of tools and techniques pushes the whole field forward. It highlights how the quest for knowledge is always a moving target, always building on the past but reaching for the future. Hashtag tag tag outro.
And there you have it. We've journeyed through the monumental, The Theory of the Riemann zeta function by Titchmarsh in its second edition, so carefully revised by Heath Brown. We've seen its foundational strength, its incredibly comprehensive coverage of the zeta function's intricate dance with prime numbers, and its deep dive into the very heart of analytic number theory, including that still unsolved, still beckoning Riemann hypothesis. It really is a definitive encyclopedic reference, a truly colossal achievement for its time. That crucial timestamp of 1987.
It absolutely stands as a testament to rigorous mathematical scholarship. It's an essential resource, really indispensable, for anyone seriously delving into the zeta function and the profound mysteries of prime numbers. But its value isn't diminished by what came later. Not at all. Rather, it serves as the bedrock, the essential foundation upon which all subsequent discoveries, all those new frontiers we discussed, are built. Understanding this book is like understanding the ground floor of a vast, ever-expanding skyscraper of knowledge. It was the launch pad.
A launch pad for future generations of mathematicians to just keep pushing those boundaries of knowledge further and further.
Exactly.
So as you reflect on this incredible deep dive we've taken today, maybe consider this. If a book published back in 1987 could be so comprehensive, capturing 4 decades of absolutely groundbreaking research and pushing right up against the limits of what was known then, just imagine the sheer volume, the complexity, maybe the surprising new directions mathematics has taken in the 4 decades since then, all while the Riemann hypothesis continues to shimmer just out of reach, beckoning from the future. What groundbreaking discoveries are being made right now, today, that will one day form the missing pieces of our current understanding. Pieces that will invite future generations to update and expand our knowledge all over again.
It's a fascinating thought. The process never stops.
It really doesn't. Thank you for joining us on the deep dive. Until next time, keep exploring. Welcome.